Okay guys, in our lesson today we're going to be taking a look at using our unit circle as a tool again to help us easily evaluate for cosine, sine, and tangent values at very well known and well behaved angles here. And so really quickly let's review what we know about our unit circle. Our unit circle is a circle of radius 1 centered at 0, 0, has the equation x squared plus y squared equals 1, and recall that all points x, y on the exterior of this unit circle tell us both the cosine and the sine respectively. So really quickly here we're going to recap that our x values on the exterior tell us the cosine, our y values tell us the sine, and if you've been paying attention then our tangent value here, we say tangent of theta, that would be our y over our x. And so these values here kind of help us find the values of our trig functions here on our unit circle. What I want to be able to do is this, use our unit circle today, but what I'd also like to be able to do is not have to recall all of the points around the exterior of this because, well, there's a lot of symmetry that goes on. So what we're going to do is use a different tactic. We're going to find the value of a trig function of an angle theta in standard position, but instead by using what we call its reference angle, and we're going to call that theta prime. So I have this reference sheet here for everybody, and you'll get one when we get back to school. But for now, just know that what we're going to use is what we call a reference angle. So in terms of a reference angle, what I'm going to have everybody do is just kind of imagine a 60-degree angle in standard position here. If you were to look at a 60-degree angle in standard position, we know that this point is 1 over 2 or 3 over 2 here. What if I were to compare that angle 60 degrees to, say, a 120-degree angle here? Now, when you look at 120 degrees, of course, it terminates over here in the second quadrant. But when it comes to making a right triangle out of these things, here's our right triangle when I drop an altitude in the second quadrant. Here's my right triangle when I drop an altitude in the first quadrant. So what I want you to notice about these two triangles is that in terms of their x and y values here, it looks like they have the exact same distance of x and the exact same distance on y. The difference here is on one of these we had to go right and up, the other one we had to go left and up. So if I had to say how would the point over here, this point here compare to the ordered pair over here, I would say, well, that it still have to be a half for my x, it still have to be root 3 over 2 for my y. It's just that my x value would have to be negative because I determined to terminate in the second quadrant there. So you can see that any of these triangles that make a 60-degree angle right here, 60-degree angle, 60-degree angle, if I made another 60-degree angle here with the x-axis, all of these triangles would basically be congruent. So what I want to do is focus on, in terms of our angles here, what kind of angles do we make with the x-axis? Because as long as I know that angle you make with the x-axis, then I kind of know what values you would have just by looking at this up over here. So I've got a lot to undo here. I'd like to get a lot of this out of the way here. Essentially, though, what I want to bring up first is this idea of the angle we make with an x-axis. So we're going to give this a name. We're going to call this our reference angle. So really quickly here, let's go ahead and write down the definition of what we mean by a reference angle. And then we're going to define a few reference angles here. We say a reference angle. Let's see if this will type here for us. The positive acute angle. Oh, let's write here. Let's try this again. Thanks for being patient with me, guys. We say a reference angle. The positive acute angle formed between the terminal side of theta and the x-axis. And so this is kind of a fancy way to say, hey, this is the angle you make with the x-axis here. But what I want to do really quickly, just kind of look at some reference angles. So down here, what you're going to see are 4 diagrams in which our original angle, what we call theta, okay, is going to be graphed in green, and our theta prime, which is what we refer to as our reference angle here, the angle we make with the x-axis, is going to be in red. So you're going to notice that there are 4 angles here, and each of these angles in green either terminates in quadrant 1, quadrant 2, quadrant 3, or quadrant 4. But what you're also going to see is this. At every possible instance, you're going to see wherever the terminal arm is on your image, that our angle makes an angle with the x-axis that is an acute angle here. And so we're always going to be kind of after this angle you make with the x-axis right here, just because I know that I would have the same values as my reference angle here at my original angle. So they all kind of make congruent triangles. When you drop altitudes, we want to be after what is that red angle there. And so we're going to write 4 different definitions for theta prime down here. And in terms of definitions, what I mean is, what if I knew theta? How could I find theta prime? So the first thing I want you to notice is this. If you terminate in the first quadrant, then your reference angle, theta prime, is going to be the same as the initial angle to begin begin with here, just because they make the same angle with the x-axis. However, if you terminate in the second quadrant, keep in mind this is 180 degrees or pi radians here. If we want to find this reference angle here in red that it makes with the x-axis, we're going to have to say that our reference angle then would be 180 degrees minus the angle that we were given. Another way to write this is 180 degrees or pi radians minus the angle we're given if you're working in radians. When you look down here in the third quadrant instance, this is actually, say this was like a 240 degree angle. We still know this is 180, except for this time I'd have to do 240 minus 180. So this would mean that our reference angle is really the angle that I'm given minus the 180 degrees part, or we could say, if I want this in radians, we could say the angle I'm given minus pi radians. And then the last one here, let's say this was, say, a 300 degree angle here. It would make a 60 with the x-axis, but because we'd have to take 360 minus the 300. So in other words, our reference angle here is always going to be 360 minus the angle we're given, or if you're working in radians, 2 pi radians minus the angle we're given. Here's what I need you to know. We're going to be using this angle that it makes with the x-axis here in order to determine the value of a trig function. So in terms of what I want you to learn today, we're going to use this reference angle theorem. And in a nutshell, it says this: the reference angle theorem states that to find the value of a trig function of an angle theta, we could just use the reference angle instead. So determine the function value of the associated reference angle, theta prime, and then depending upon the quadrant in which theta lies, the answer is either going to be positive or negative. So really quickly, let's kind of supplement that over here. Remember that all of our points in the first quadrant, x and y, are positive. We have negative x's, positive y's in the second. We got negative x's and negative y's in the third, and then positive x's but negative y's in the fourth here. So what this is going to mean is we use this mnemonic, all students take calculus, to kind of help us understand which trig functions are positive in the different quadrants here. And the reason why I bring up that all students take calculus is because it helps us remember that all of our trig functions are positive in the first quadrant. Sine's positive, cosine's positive, and then sine over cosine, y over x would be positive. So that means that in the first quadrant, all of our trig functions are positive. In the second quadrant, the only thing are positive are sine and its reciprocal cosecant. Why? Because we have a positive y, and keep in mind sine values are our y values here. So in the second quadrant, sine is positive, cosine and tangent are negative. When you look down here, tangent is positive because y over x would be a negative over negative is positive. Sine and cosine would be negative, and down here cosine would be positive because x is positive, and x values are our cosine values here. It's just that our sine values and our tangent values would be negative. So using that, we can determine as our second step here, after we use our reference angle to evaluate our function, whether or not our function would have a positive or negative value. So here's what I want to do. I want to look at a couple of examples with you here, and then each of you in our different classes here have different assignments to work through, but all of them involves using a unit circle to evaluate trig functions such as these two you see here. So we're going to break this down into four steps that I want you to use every time, and it's going to involve using a reference angle instead. So it says find the reference angle theta prime for the given angle is going to be our first step here. Well, when you look at secant of negative 5 pi 6th, I think I want to keep in mind that when we talk about pi 6, these are 30-degree rotations, so it would take 6 of them to get around to pi, and it would take another 6 around to get to 2 pi here. But if I had negative 5 pi 6, we would rotate clockwise 5 of these, and so that would drop us right here. Here is essentially going to be our angle there. So the question is, what angle does this make with the x-axis? The first thing I notice is that it makes a theta prime angle of pi 6, the 1 pi 6 radian measurement. So here's the deal. When it comes to evaluating these today, the idea is going to be that instead of using the angle that I give you, I kind of always want you to use just the angle it makes with the x-axis here. The next thing I want to do is, number 2, rewrite the original trig function with the reference angle theta prime. So you see I've done that here. Step 3 is going to be to fix the appropriate sign to the trig function, plus or minus depending upon which quadrant the angle terminates in. So that's going to mean that we would kind of split this up into 4 quadrants and use this all students take calculus approach. But I noticed that this terminates in the third quadrant, and the only functions positive in the third quadrant are tangent or cotangent, which would mean my secant value here is negative. So here's where we've done the fixing. We have fixed a sign here. The last thing is going to be evaluate the trig function. So now the advantage to using the reference angle here, pi 6, is that when I fill out this unit circle on my paper, I tend to have a tendency to only fill out the first quadrant and then these 4 points. So we have 1, 0, negative 1, 0, 0, 1, and 0, negative 1, just because it's the unit circle. And then remember these 3 angles out here, these involve 2's on the bottom, and then it goes 1, 2, 3. Down our cosine values, 1, 2, 3, going back up our sine values here. So this is going to be as easy as go look at pi 6 here, which is this measurement here, and we want the reciprocal of cosine. So if this is root 3 over 2, we're going to say that this is 2 over root 3. That's our secant of pi 6 value, and we had a negative that went out in front. So we really get negative 2 root 3 over 3 when we rationalize it, but you can see that this was a lot easier done with just the reference angle here. So let's try this again, just these 4 steps. Starting with number 1 here, it says, given the angle here, we want to find and use the reference angle instead. When you think about a negative 405, that'd be at least a negative 360. Plus, if you use a calculator here, 405 minus 360, suppose we would find out that that's 45 degrees past 360. So it's kind of like this idea that it would wrap around once and then land here. Here's our negative 405. Remember, the idea today, though, is going to be what's the angle it makes with the x-axis? What's this positive acute angle right here? And so because I know my theta prime is 45 degrees, what we're going to do is we're just going to rewrite this as the tangent of 45 degrees. So we've got step 1. Find the reference angle. Step 2, just rewrite it using the reference angle. Step 3 is going to be, should this be plus or minus? And looking at this quadrant that it terminates in, I know that cosine functions and secant functions are positive down here, but this is tangent, so this is going to have to be negative. So what's our tangent at a 45? Recall that with your tangent values here, these are y over x. So our tangent at a 45, root 2 over 2, divided by itself is always going to be 1. It's good to also recall that our tangent of a 60 or a pi thirds is root 3, and our tangent of a 30 is root 3 over 3. So we're really just going to get 1 here. I'm going to put 1, and it would have to be a negative 1. So the idea today is going to be that I want you guys, instead of using the original angle here and thinking about what have to be true about your values on the outside of the circle, we're going to use a reference angle instead, and then put a plus or minus depending upon what quadrant it terminates in. Last note is going to be this. The only time I don't use a reference angle is if it lands exactly at north, west, south, or east, or any of those multiples there. You can just use these outer values to evaluate your functions here. Okay? Cheers.